In this lesson, the aim is to develop our understanding of how the mass and volume flow rates vary as fluid flows through a gradually tapering pipe. Now, the diagram that you see on screen here is what we're going to use to develop our understanding of this concept. And what you're looking at here is a gradually tapered pipe. We're coming from the left right there. We have V1. And that's representing the initial velocity. And if we go over to the right there, where we have V2, that's representing our final velocity. And we're going to also take into consideration the areas on both ends. So A1 right here for the initial area and A2 for the final area. So these are three typical questions that you would get asked, where we need to analyze a system like this and find either the initial velocity or the final velocity, and then the volumetric flow rate as well as the mass flow rate. So say we're given a diameter for A1, and that's given as 100 millimeters. And let's say another diameter given for our A2 section as 80 mil. And the final flow velocity given as 12 meters per second, given that we're going to find the initial velocity. Now, with this information, let's work out first of all what our initial velocity is going to be. So to find our initial velocity, we first need to work out A1, which is the initial area. And we can use the given diameter to do that. So if we use this formula, pi times diameter squared divided by 4, then that will allow us to find what A1 is. And since our diameter is 100 mil, then we can just convert that to meter, and that will just be 0.1 meters. And if we square that and divide by 4, then we get A1. And A1 turns out to be 7.85 times 10 to the negative 3, and our unit is meters squared. So that will give us A1. Now we do the same thing to find what A2 is. So we have A2 as 5.03 and times by 10 to the power of negative 3 meters squared, and that's just representing our answers in standard form. So now to evaluate what our initial velocity is, we use this formula. A1 times V1 should be equal to A2 times V2. And if we were to just rearrange this then, so we have therefore V1 should be equal to A2 times V2 and all divided by A1. And we have all of those values, so let's plug them in and find what our V1 is. So 5.03 times 10 to the negative 3 there for our A2 value, multiplied by 12 meters per second, and all divided by our initial value there for A1, 7.85 times 10 to the negative 3. So we have an initial velocity here of 7.68 meters per second. So this is representing our initial velocity. So to go on then to evaluate our volumetric flow rate. So for this, the symbol is Q with a dot above it like that. And it's equal to, we can either use A2 times V2 or A1 times V1, as they should give us the same answer because we have a steady flow system. So our answer here is 5.03 times by 10 to the negative 3. And this is representing our A2 value. If we multiply that then by our velocity there, V2, then what we have is 91.80 times 10 to the negative 3. And this is meters cubed per second. So this is representing our volumetric flow rate. So this figure tells us how much in terms of volume per second is flowing through our system here. So the final piece of the puzzle is to work out our mass flow rate. So for the mass flow rate, what we have here is this common m with a dot above it equals to our density times volumetric flow rate. And say we're dealing with water, our density would be 1000, and if we multiply that by our volumetric flow rate, then what we have here is our mass flow rate, and this is equal to 91.8, and unit for mass is kilograms, so kilograms per second. So that's it for our 3 variables. Now, if you would like to see more content like this, please let me know in the comment section, as I am really looking forward to do a lot more videos like this, but obviously I want them to be as useful to you as possible. So please share with me in the comment section what other topics you would like me to cover.